All right. So we're back in the wonderful world of column design, which we're probably going to finish today, and then we're going to hopefully get into beam columns. So real quick, a couple handouts up here. I've got one handout on compression members, axial load only, and then a homework 8 in case anybody's missing it. Remember that homework is due on Friday. I just handed out the beam column set of notes. So yeah. Let's see. Here, keep the sign-in sheet with the notebook. That way, you know. All right. Okay. So real quick, let's get back into what we were discussing. Let me get my notes here sort of lined out. We are getting close to the end here. It's kind of nostalgic, you know. As a joke, not a very funny one. What's that? Striking out. Yeah. I guess it's just because it's Monday. And it's the last week, and you're like, please, God, let me get out of here, right? I can't take any more of this dry, horrible humor anymore. I'm getting tired of it. It's been a solid year of this crap. What's that? You're about to crack? Hey, these folks have me back to back, so just saying. All right. I don't even know what that means, so I'm gonna move on with that one. Okay, all right. So column design. We did a column design problem last time, and ultimately I think it's a pretty straightforward process. We determine the design load. We guess a reinforcement ratio. A good starting value is 0.02 unless you are otherwise dictated. Solve for the gross area, then take that gross area and plug it back into the expression to solve for the steel. Select the amount of steel, check your details, and that's about it. So there's your equation for the minimum gross area. Once you get that gross area, select some dimensions, solve for AST minimum. That's about it. So we did this one last time. We designed a square column to resist those loads, used 2% steel, and so on and so forth. Pretty good, right? Okay. Now we're going to do the same thing, only we're going to do a round column, a round spiral column. So it's going to support a dead load of 240 kips, a live load of 300 kips, and the material properties are the same. And the process is, for the most part, going to be fairly identical. It's not going to be anything greatly, brand new. So, all right. So, all right. So let's go through some column parameters. All right, so FC prime, 4 KSI, FY, 60 KSI. Now our rho G value starting for design is what? This is our starting value for design. What? There you go, 0.02. You both got it. Yeah, we're assuming 2% steel to start out with, okay? A dead load, 240 kips. A live load of 300 kips. And that's what we got. What's first step? What's the first step in every single design problem we have done this entire semester? Factor the loads. And drum roll, 1.2 dead plus 1.6 live. And what do we get? 768. All right. Now, this is a circular or a spirally reinforced column. So, what's phi and alpha? There we go. So, therefore, gross area. All right. So our AG min is it's a big fraction on the bottom, so phi alpha and then 0.85 FC prime 1 minus rho g plus Fy rho g. So bless you. So we are assuming a reinforcement ratio and using that assumed amount of reinforcement to figure out, okay, if that's how much reinforcement we were given, what's the required area of our concrete? And all that's under, all that's under PU. So 0.75, 0.85. Actually, I'm not going to be able to fit this. Let me. Zero 0.75, 0.85, 0.85, 4 KSI, and then 1 minus 0.02. And then this is, all right, I may have a typo in my little handout here, so let's just see what you all get. Anybody calculated this out? $265.8. Anybody else getting that? All right. Guess I don't. I guess I just wrote something down wrong. Okay. So that's how much area we need for our column. What is the shape of this column? Circle, right? So what is the area of a circle? What's that? Something with pi. I think that's the answer to about 65% of all engineering questions. There's pi in there somewhere. All right. The area is pi d squared over 4, right? So therefore, if I wanted to compute the minimum diameter, would it be 4 times the area divided by pi square root, right? Take the 4, move it up here, divide the pi, square root, there you get d squared, square root, that gives you d, right? So, everybody okay with that? So, 4 times 265.8 divided by pi, 3.14, all that jazz. What do we get? 18.396 inches. Now, I'm going to do something that might seem a little odd. Instead of rounding up, I'm going to round down. And I'm going to say, let's use an 18-inch column. Okay? There's a reason for that. Okay? So let me put that down there. Whoop. There's a reason for that. Because what I'm going to do is I'm going to use this D, and I'm going to compute what is the actual gross area of the column. And then I'm going to use that actual gross area to compute how much reinforcement I need for that column to resist that load. Point is, this whole calculation, this AG-min calculation, was based on an assumed 0.02 reinforcement. It can vary a little bit. I could throw a little more reinforcement into this column as opposed to a little less. Here's the reason why I'm doing this. What would I do? Round this up to 19 inches? Does a 19-inch round column make a lot of sense? I mean, if I rounded it up to 20 inches, that might make sense, but I mean, now I'm using a whole lot more concrete than I really need. If all I end up doing is throwing an extra bar into this column, ultimately, it's probably going to be most economical. Plus, a lot of round circular columns, you're using pre-made formwork that comes in pretty standard increments. I mean, try find a form for a 19-inch column. 18 inches, that's pretty common. Okay, does that make sense? All right, so again, we made an assumption to arrive at this dimension. So there's no problem going up or going down as long as you use the actual gross area to compute what is the required steel. Okay? If I took this, here, hold on. Everybody got what I need over here? Or everybody got what you need right here? All right, can I go on to the next panel? See, let me explain. All right. Excuse me. All right. So the diameter of this column is 18 inches. Therefore, the area of this column is pi d squared over 4, which is what? Okay. Here's the point. I have a column. If I took this column, if I did this, if I said the required area of steel is just that column times that 0.02, if I did that, that would be dead wrong. Okay? The reason why is because I took my column and I undersized it a little bit. So as a result, the amount of steel that's going to be required goes up a little bit. How do I determine how much steel is required? I use this. Bless you. When we back calculate our reinforcement ratio, we're going to find that we ended up increasing it a little bit. So let's go through this. So 768 minus, what do we have? 0.75, 0.85, 0.85 again, because we have alpha and then the 0.85, 4 KSI, and then 254.5 inches squared. And then what do we have? We have 0.75, 0.85, 60 KSI minus 0.85 4 KSI. Well, what do we get? 5.99. So what do you think is a appropriate amount of steel to go into this column? Without even going to the charts. It's so close to what? 6. How about 6 number 9s? There we go. All right. Take this and just multiply it by 0.02 and tell me what you get. 5.09, right? That is why we're able to take the column and make it a little smaller, because we're using that smaller column size and we're determining how much steel we need for that column size, okay? If we just used our assumed row value, we get the wrong answer. Now we're actually directly computing it. So that's the logic behind why we're able to do that. All right? Does that make sense? All right. Excuse me. All right. So let me ask you this. Let's look at spiral columns. If you have a spiral column, what's the minimum amount of bars you're allowed to have? What's that? 6. So we're good there. The only thing we need to do is select the amount of spiral reinforcement. That's it. And I'm going to tell you about 999 times out of 1,000, it's going to be number 3s at 2 inches. And you're going to see why. Watch this. Okay. So we're going to start off with our spiral selection by trying a number 3 spiral, which is a pretty standard choice. Okay. Now, we're also going to use 1.5 inches of cover. Okay, which is a pretty standard selection. So therefore, the diameter of the core is going to be 18 inches minus 2 times 1.5, cover on each end, which comes out to be 15 inches. So that means the area of the core is pi d squared over 4, the diameter of the core. And so that gives us 176.71. Or if you want just 176.7, it doesn't matter. Okay. Now, I'm going to select the amount of reinforcement or the spacing based on our reinforcement limits. So let me show you something. So rho S minimum, that's the minimum percentage of steel that we can have, is this. Or AG. Ooh. Butchered that. Okay, so that is the absolute minimum amount of steel that we are allowed to provide. So plug and chug. All right. Y'all remember that from last time, right? The limit on spiral reinforcement. Okay. That comes out to be 0.0132. Is that about right? Okay. All right. Has everybody got this? Everybody got what they need? Can I go ahead and move on? Okay. Did you need? Okay. You sure? All right. It's recording, so. All right. So rho S minimum was 0.0132. Okay? Now, how do you compute the actual rho, the actual reinforcement? Remember this? Or wait, whoop. Remember that? Okay, remember how we compare the limit against what's actually there? Well, what I'm going to do is I'm going to use this, and I'm going to solve for, well, if I'm using number 3 stirrups, what does my pitch need to be? Okay, we'll see what we get there. And what we'll see is this. All right, the diameter, I'll put this over on the side. The diameter of a number 3 is 3/8 of an inch, and the area is 0.11 inches squared. So watch what I'm going to do. I'm going to solve for S, and we'll move that over here, bring that down. I'm going to say, all right, therefore my S max is just which is, hold on, give me 1 minute. Okay, good. 4 times 0.11 inches squared, 15 inches minus 3/8, 0.0132, 15 inches squared, which is plug and chug, and that gives you 2.167 inches. So just so we're clear on what it is we're computing, what we're determining is we're saying, all right, I assumed a number 3 spiral. I say, all right, I got a number 3 spiral, and then based on that number 3 spiral, if I want to provide adequate spiral reinforcement, I have to use a maximum pitch of 2.167 inches or whatever. So what would be a good value for the purposes of design? 2 inches. So what's the answer? Oh, I hate drawing these circles. All right. That's not bad. It's about the best you're going to get from me. Okay. So we have a column that is 18 inches in diameter. We have a cover distance of 1.5 inches. We have number 3 spirals at 2 inches, and we have 6 number 9s. And that is column design, ladies and gentlemen. Lady and gentlemen. All right. Does anybody have any questions? Everybody good? Okay. Last topic of the semester is coming up. Y'all were just thinking like, oh man, we're done. No, we got one more. When will it ever end? No, last class is Friday's just review, exam review. All right. Okay. So what we're going to discuss today is the concept of beam columns. Okay. Now, my steel design folks have already touched on this type of analysis before. In steel design, we discussed the concept of interaction when we looked at bolts that were subjected to shear and tension. And the idea was, well, you want to compute, you want to look at the capacity in shear, you want to look at the capacity in tension, and now you want to look at the capacity of both, of them interacting. But if you haven't had steel design, then this might be somewhat of a new topic. So I want to kind of, explain this topic from a new standpoint, okay? So I want to talk about this concept of interaction. What does interaction mean, okay? Let's look at this, okay? This is the fundamental expression of everything that we have been doing this semester. This is the famous LRFD design expression, the fact that your factored resistances must be greater than or equal to your factored loads, okay? Now, if all we're looking at is columns subjected to an axial load, we say, all right, phi Pn has to be greater than or equal to Pu. What I might do is I might say, all right, let's try and deal with this non-dimensionally and divide everything out. So would you agree that another way of writing that is this? So I might say, all right, that the load over the resistance, that ratio must be less than or equal to 1. Is that a fair point? Okay. Now, that would be great if you've got a member subjected only to an axial load. Now what about this? Now I put a bending moment on there. I can write a similar expression for this, and I can say, all right, here's the bending moment contribution. So what I might say is I might say, all right, well, if Pu over phi Pn has to be less than or equal to 1, and Mu over phi Mn has to be less than or equal to 1, I might say, all right, well, I can't expect the full capacity of the bending and the full capacity of the axial load all at the same time. So I might come up with what I'll call a simplified interaction relationship, which basically means that, however much axial capacity I'm demanding and however much moment capacity I'm demanding, the sum of those can't be greater than or equal to 1. That's a simplified interaction relationship, okay? The problem is that doesn't work. It greatly underestimates the capacity of beam columns. And what I'm going to do is I'm going to show you a different way of developing an interaction relationship, which is also called a PM curve, if you ever hear the term PM curve, because P for axial load, M for moment. There's a different way of going about it. And I'm going to show you how PM curves are derived, bless you, using some of the stuff we have been looking at all semester, okay? So let's take a look at this, okay? I have here a column that is 18 inches by 18 inches. It's square, so everything's nice. The cover everywhere on the bars is 3 inches, okay? And each of the bars are number 9s. They're 1 square inch, okay? And for the purposes of what we're doing, we're going to assume bending about the x-axis. What I'm going to do is I'm going to generate some points that we can use to draw a PM curve, okay? Now, let's start off with the simple one, Let's start off with the case where you have nothing but axial load on it. If all you have is axial load and no bending moment, well, that's simple, right? Just calculate the theoretical capacity. For now, I'm ignoring the 0.8 for that accidental eccentricity, and I'm ignoring the phi value. We're going to apply that later, okay? Sound good? Okay. Now, that's pure axial load. What about pure bending? How do you determine this? Well, if this is pure bending, isn't this a doubly reinforced beam? A beam where you have tensile reinforcement and compression reinforcement? Remember we did that way back when? Remember a doubly reinforced beam, and then you had to do that quadratic expression to figure out where C was, and then some moments. Remember that? That's why I'm bringing. That was one of the main reasons that we did that, so that you all would recognize this now. Okay? Does that make sense? Okay. So if you've got pure bending, okay, we do the same thing we did before. Remember, we had that quadratic expression. We solve for C, using your Casio or whatever, get a C value, and then we say, all right, here's your nominal moment capacity, so on and so forth. Okay? So now we've got 2 points on our interaction diagram. In other words, if I draw an interaction diagram that looks something like this, oh, now, this doesn't like me right now. If I draw an interaction diagram, let's see if this works. And I say P on this axis, M on this axis. I've got 2 points. I've got the case of pure axial load. This would be where M equals 0. And then I've got the case of pure bending where P equals 0. So this would be like 141.65 foot kips right here. Does that make sense? Everybody okay with that? Now, we'll go ahead and erase this. Okay. Okay. Where's my mouse? Okay. So that's 2 values on the curve. How do we get the values everywhere else? And if like when I teach an advanced concrete design course, this is one of the first things I have them do is actually write an Excel sheet that automatically does this calc, because it's not very difficult. You just got to be careful with your bookkeeping. Bleh. So how do we get the curves or get the values everywhere else? Well, what we do is we say, all right, let's just make a guess. Let's assume where the neutral axis is. And we say, all right, based on that neutral axis, we can determine what are the strains in the steel. We can determine what are the stresses in the steel. We can also determine the forces in the steel and the concrete. And then all we got to do is use equilibrium to figure out what's the axial force and what's the moment. I'll give you an example. Okay? Let's just make a guess. Just completely guess. Let's just make a guess of C being 11 inches. Okay? If C is 11 inches, remember this, 0.003 D minus C over C, and then 0.003 whatever. I can use that guess to determine what is the strain in the top layer of steel, what is the strain in the bottom layer of steel. Now, in this instance, I've got a situation where the top layer of steel has yielded, the bottom layer hasn't, right? Make sense? So what's the stress in the steel? For the top layer, it's 60 KSI because it's yielded. For the bottom layer, it hasn't, so it's E times the stress. Make sense? All right. So what are the forces? Well, for the concrete, it's 0.85 FC prime AB, right? Or 0.85 FC prime A, which is beta 1 times C. And then what's the force in the steel? Well, it's the stress times the area. Okay. So far, so good? Now, some of you might be thinking, well, what about sum of forces in the x direction? Don't all my forces in compression have to equal all my forces in tension? Not when you're looking at beam columns, because with beam columns, there's another force. There's your compressive force in the steel, there's the tensile force in your steel, there's the compressive force in the concrete, and there's the force being applied. That's where the equilibrium comes into play. So how do you determine excuse me, how do you determine the compressive or the axial load, the load that member can resist? just some forces in the x direction. Taking compressive forces to be positive, I submit that this column under this condition can withstand about 680 kips of axial load and compression. As for bending moment, I just sum moments about the centroid. So force times distance, force times distance, force times distance. Does that make sense? And that was based on just a random guess of C equals 11 inches. So what I do is I just make more guesses. Excel is really, really nice to define curves like this. So what ends up happening is, you put C equals 11, C equals 12, C equals 13. Just make a bunch of guesses, right? Based on all those guesses, we can plot something that looks like this. So this is a typical PM curve for a column. And one of the things that's kind of interesting is that these curves, if you take a look at it, are kind of the genesis, if you will, of the concept of pre-stressed concrete. See, go back to that column. Under pure bending, no axial force at all, it could withstand a moment of about like 145, was it? Something like that? But if I put some axial load on that section, it can actually resist more bending. In fact, it can get all the way, almost twice that value. It could, with no axial load at all, about 140. But if I put in a little bit of compressive load in there, that bending capacity, in fact, more than doubles. Okay? How do you pre-stress a beam? I'm sure you all have heard of this concept before. The idea is you take an element of steel and subject it to a lot of tension. Okay? Now, if you're pre-tensioning, you subject it to tension, you cast concrete around it, you cut the cables. What happens to the beam? It locks in that compressive force. By locking in that compressive force, you take that beam and you make it stronger. By taking that beam and making it stronger, you can make it smaller. That's the concept of pre-stressed concrete. Now, there is a whole lot more that goes into it because there's losses and all sorts of stress checks that need to be done. But in the end, that's the general concept behind what is going on. But if we're talking about just general building design and general elements, certain levels of compressive force can actually serve to increase the bending capacity of a given section. Why is that? Concrete is a material that is very, very strong in compression, but very, very weak in tension. And what you're doing is taking this member and putting more compression on it. You're putting the force on it that concrete loves. Okay? Does that make sense? So that's why it behaves better. Now, this is your nominal PM curve. I'm going to do two things to it. First thing I'm going to do is I'm going to cut it off at the top. I'm adjusting it by that 0.8. That accounts for that accidental eccentricity. Okay? So that's my nominal cutoff curve. Now, these are all nominal values. What must I then do? I must apply phi, my resistance factor. Now, if you notice, look here, look at the compressive load, or the axial forces. It went from about like 1050 to like almost 700. That reduction right there was the 0.65, where phi is 0.65 for columns. But here, on the bending, if you look here, we go from about 145 to about 130. We don't reduce as much. That's because, remember, under pure bending, phi is 0.9 when you're tension controlled. Y'all remember that? I know you do. I know it's the last week of the semester and you're like, oh, God. What dramatically increase? Oh, that's a good question. Why is there this hump? The reason why is because of your phi values. All the way up here, it's a constant 0.65. Hold on. Let me go. I'm going to go way back 308. The reason why is this. Because you're in that transition region where phi isn't changing, or it's changing, so it's not changing your capacity as much, or it's changing it at a different rate. That's a good question. Does that make sense? Now, I'm not going to get too crazy into the theory because we could talk about this all semester, but this peak out here at the very end is what's called the balance point. And it's that magical point where the strain in the steel equals the strain at yield. But That's just food for thought. Okay, so how do you design beam columns? And I should have brought my PM curves with me, but I'll bring them on Wednesday. The idea is that beam column would be highly iterative if we didn't have any tools for design. Luckily, we do. We have a number of design aids available. They're actually in the back of your book, and essentially they're PM curves. They look something like this, okay? You might have been flipping through the back of your textbook and seen these. These essentially are PM curves, okay? Now, the one on the left is different than the one on the right because they're different columns. This is looking at rectangular columns, and this is looking at circular columns. So the math and the mechanics are a little bit different. Now, what they have done to, what ACI has done to generate these PM curves is generated them based on these dimensionless parameters. So this Kn and this Rn, this Kn is sort of related to, I guess I'll call it the percent axial load, and this Rn, the percent bending on the section. So what you would do is you would calculate a Kn, a Pn, go into this chart, find the reinforcement ratio that's right for you, and there you go. Excuse me. So let me explain a little bit about how these design aids work. So if you look here, let me go back a slide. If you look here, there's interaction diagram, and then here on the left, it's L4-60.6. And then over here, C4-60.8. Does everybody see that? Okay. So the L stands for rectangular columns that have 2 layers of steel. The R are rectangular columns that have 3 layers of steel. So an R column would have bars here and here, like right there. Okay? And C obviously stands for circular columns. Now, the 4 and the 60 stand for the material strength. So we're looking at 4 KSI concrete, 60 KSI steel. The 7 refers to this gamma, gamma being like a percentage of the height. So it's basically your distance between your layers of rebar. So if you were looking at a 0.7, it would say that that ratio, or that ratio between the bar lengths and the total height of the beam would be about 70%, or would be 70%. Does that make sense? We'll have a little bit of practice with this, but this is how this works, okay? You determine your factored moment, determine your required Pn and Mn. You assume a phi value right off the bat, determine your eccentricity, which we'll go into this next time, your eccentricity and your gamma. Based on those, compute Kn and Rn, Kn and Rn, go into the chart, figure out your reinforcement ratio, calculate the amount of steel, and that's it. It's really pretty simple. Without these design aids, this would be a very nasty process, okay? Because there'd be a lot of iteration. If you steel folks who thought that column Excel chart sucked, that was nothing compared to this. So the idea is there would be a lot of nasty Excel work, okay? But what we're going to do is we're going to do this example next time, and I'm going to take my time with it. But the idea is, here's the column. We know the dimensions of the column. We know the loads on the column. Based on these dimensions and these loads, I want to determine how much steel needs to go here and here. Now, I have 3 bars. I'm not saying that you must pick a bar here, here, and here. I'm just saying that there's 2 layers. You can have 8 bars here and 8 bars here. I'm just saying there's 2 layers of steel, okay? I will give you the beam column charts next time, and we'll go through this example. We'll probably end class early because this is not a long example, and then that's it. Reinforced concrete design is over after this example. I don't know if we have enough time. And plus, y'all have a homework due on Friday. We'll see where we get them. Plus, we're still going to be here on all day Wednesday for steel. See now, what if I get lazy with my video posting? Oh man, that just took too much time. Oh. Am I holding your education hostage right now? Is that what I'm doing? All right, that's all I've got. I will see you all next time.